Download this code from codegive.com, link in the description below. OK, let's delve into the world of llama, specifically llama 2, its integration with NDC, Neural Device Compiler, and explore how you can leverage it within the Porto framework. I'll provide explanations, code examples, where applicable, and discuss the trade-offs involved. Llama 2, a deep dive. What is llama? Llama, Large Language Model Meta AI, is a family of open-source large language models developed by Meta AI. Llama 2 is the successor and improves upon the original Llama with larger data sets, better training methodologies, and a more permissive license, allowing commercial use. Key features of Llama 2 open source and commercial friendly. The most significant advantage of Llama 2 is its open source nature with a license that allows for commercial applications, subject to certain terms depending on the size of the organization using it. This makes it a compelling alternative to closed source models like those from OpenAI and Google. Variety of sizes. Llama 2 is available in a range of parameter sizes, 7B, 13B, 70B parameters, which allows you to select a model that balances performance with computational requirements. Fine-tuning potential. Llama 2 is designed to be fine-tuned on specific tasks or data sets. This allows you to adapt the model to your specific use case, improving its performance on those tasks. Improved reasoning and knowledge. Llama 2 generally exhibits improved reasoning capabilities and a broader knowledge base compared to its predecessor. However, like all LLMs, it is not perfect and can still make mistakes or generate inaccurate information. Chat versions. Meta also released Llama 2 chat models. These are specifically fine-tuned for conversational applications, chatbots, virtual assistants, etc. They have been trained with reinforcement learning from human feedback, RLHF, to generate more helpful, safe, and engaging responses. Technical details. Architecture. Llama 2 is based on a transformer architecture, a standard architecture in modern LLMs. It uses a decoder-only transformer, meaning it predicts the next token in a sequence based on the preceding tokens. Training data. The models were trained on a massive dataset of publicly available text data. Meta has emphasized a focus on removing personally identifiable information, PII, from the training data. Pre-training and fine-tuning. Llama 2 is initially pre-trained on a large general-purpose corpus. Then, the chat versions are fine-tuned using RLHF to align the model with human preferences for helpfulness and safety. Accessing Llama 2. You can access Llama 2 through several avenues. Meta's website. You need to request access from Meta, via their website, to obtain the weights. You'll need to agree to their terms of use. Hugging Face Hub. Once you have access, the models are available on the Hugging Face Hub. This makes it easy to download and use them with the Hugging Face Transformers library. 2. NDC, Neural Device Compiler. What is NDC? NDC is a compiler that allows you to target different hardware platforms, GPUs, TPUs, CPUs, with your neural networks. It takes a high-level representation of your model and optimizes it for the target hardware, potentially leading to significant performance gains. While NDC isn't directly a standalone product easily used by everyone, its technologies and concepts are often incorporated into frameworks like JAX and PyTorch via XLA, accelerated linear algebra. NDC's role with Llama 2 *. NDC, or XLA-like technologies, becomes important for Llama 2 because these models are computationally intensive. Running Llama 2, especially the larger versions, requires efficient hardware utilization. NDC helps in the following ways. Optimized kernel generation. NDC can generate optimized kernels, low-level code, for the specific operations in Llama 2, example matrix multiplication, attention mechanisms. These kernels are tailored to the target hardware's architecture, leading to faster execution. Graph compilation. NDC can compile the entire Llama 2 model into a computation graph. This allows for optimizations such as operator fusion, combining multiple operations into a single one, and memory allocation optimizations. Parallelization. NDC can help with parallelizing the computation across multiple cores or devices, taking advantage of the parallelism offered by GPUs and TPUs. Quantization support. Quantization reduces the memory footprint and computational cost of the model by representing weights and activations with fewer bits. NDC can help with quantizing Llama 2 models for deployment on resource-constrained devices. How it works, simplified. 1 Model definition. You define your Llama 2 model, example using PyTorch, JAX, or TensorFlow. 2 Graph representation. The framework, example PyTorch with Torch Dynamo or JAX, converts your model into an intermediate representation, a computation graph. This graph represents the flow of data and operations within the model. 3 NDC compilation. NDC, or XLA, takes this computation graph as input. 4 Optimization. NDC performs various optimizations on the graph, such as operator fusion, memory allocation, and device placement. 5 Code generation. NDC generates optimized code, example CUDA kernels for GPUs, that can be executed on the target hardware. 6 Execution. The optimized code is executed, accelerating the Llama 2 model. Challenges. Complexity. NDC and similar technologies are complex to use directly. They often require expertise in compiler design and hardware architecture. Integration. Integrating NDC into existing machine learning frameworks can be challenging. Frameworks like JAX are designed with compilation in mind, while others like PyTorch have been adding support for it, example Torch Dynamo. Hardware dependence. Optimizations performed by NDC are often specific to the target hardware. You may need to recompile the model for different hardware platforms. 3. Porto, potentially a custom framework or project context. Context matters. The term Porto doesn't have a universally recognized meaning in the context of large language models or model deployment. It's likely a project-specific name or a framework you are using internally. Assumptions and generic guidance. Let's assume Porto is a framework or system you've built or are using for deploying and serving machine learning models. It probably handles tasks like model loading, inference execution, API endpoint management, scaling and load balancing, monitoring, integrating Llama 2 with Porto, generic example. Assuming Porto can handle PyTorch or JAX models, here's a general outline of how you might integrate Llama 2. 1 Model loading. Porto needs to be able to load the Llama 2 model weights. This could involve loading the model from a local file, example a.pth file for PyTorch or a checkpoint directory for JAX. Downloading the model from a remote storage location, example a cloud storage bucket or the Hugging Face hub. 2 Inference engine. Porto needs an inference engine that can execute the Llama 2 model. This could be *PyTorch*. If Porto supports PyTorch, you can use the transformers library from Hugging Face to load llama 2 and perform inference. *JAX/Flax*. If Porto supports JAX/Flax, you can use the Flax library to load and run llama 2. *ONNX runtime*. You could convert llama 2 to ONNX format and use ONNX runtime as the inference engine. ONNX runtime can often leverage hardware acceleration. 3 API endpoint * Porto needs to expose an API endpoint that allows clients to send text prompts to llama 2 and receive generated text. 4 Pre and post processing * You'll need to handle pre-processing of the input text, example tokenization, and post-processing of the generated text, example detokenization. The Hugging Face Transformers library provides tokenizers for llama 2. 5 Hardware acceleration * To get the best performance, you'll want to enable hardware acceleration, GPU or TPU, within Porto. This typically involves *moving the llama 2 model to the GPU using .2, CUDA, in PyTorch or appropriate device placement in JAX. Using mixed precision training, example torch.cuda.amp in PyTorch, to reduce memory usage and increase throughput. Leveraging optimized libraries like CUBLAS, CUDNN, for NVIDIA GPUs, or XLA, for TPUs. Example, PyTorch with transformers and CUDA, illustrative. Explanation CUDA check checks if a CUDA-enabled GPU is available and sets the device variable accordingly. Tokenizer and model loading loads the llama 2 tokenizer and model from the Hugging Face hub, replace metallama/llama 2-7b chat hf with the actual model you want to use. The model is moved to the GPU using model.to, device. Generate _text function *. This function takes a prompt as input, tokenizes it, feeds it to the llama 2 model, generates text, and detokenizes the output. Torch.no_grad, disables gradient calculation during inference, which reduces memory usage and improves performance. Model.generate, this is the core function that generates the text. Max_length, maximum length of the generated text. Number_return_sequences, number of sequences to generate, set to 1 for a single output. Temperature, controls the randomness of the output. Lower values, example 0.2, make the output more predictable, higher values, example 1.0, make it more creative. Top_P, also controls randomness. It samples from the most probable tokens whose cumulative probability exceeds top_P. Do_sample, enable sampling for more interesting and varied outputs. If false, the model will always choose the most likely token. Key considerations for Porto integration asynchronous inference for high throughput applications, consider using asynchronous inference. This allows Porto to handle multiple requests concurrently. Batching multiple requests together can improve GPU utilization. However, it can also increase latency. Model serving frameworks consider using specialized model serving frameworks like TensorFlow Serving, TorchServe, or NVIDIA Triton Inference Server. These frameworks are designed to handle the complexities of serving machine learning models at scale. Hardware resources make sure you have sufficient GPU or TPU resources to run llama 2. The larger the model, the more resources you'll need. Monitoring monitor the performance of llama 2 in Porto, example latency, throughput, GPU utilization. This will help you identify bottlenecks and optimize performance. 4. Trade-offs. Asterisk model size versus performance asterisk. Asterisk trade-off asterisk larger Llama 2 models, example 70B, generally perform better, higher accuracy, better coherence, but require significantly more memory and computational resources. Smaller models, example 7B, are faster and require less memory but may have lower accuracy. Asterisk considerations asterisk choose a model size that balances performance with your available resources and latency requirements. Asterisk hardware acceleration versus cost asterisk. Asterisk trade-off asterisk GPUs and TPUs can significantly accelerate Llama 2 inference, but they also come with a cost, either the cost of purchasing the hardware or the cost of using cloud-based GPU/TPU instances. Asterisk considerations asterisk evaluate the cost-effectiveness of hardware acceleration based on your usage patterns and the performance gains you expect. Asterisk quantization versus accuracy asterisk. Asterisk trade-off asterisk quantization reduces the memory footprint and computational cost of Llama 2 but can also lead to a decrease in accuracy. Asterisk considerations asterisk experiment with different quantization techniques, example 8-bit quantization, to find a balance between size/speed and accuracy that meets your requirements. Use quantization-aware training if the accuracy drop is too significant. Asterisk inference speed versus generation quality asterisk. Asterisk trade-off asterisk faster inference methods, example greedy decoding, may sacrifice generation quality. More sophisticated decoding methods, example beam search, can improve quality but are slower. Asterisk considerations asterisk choose a decoding method that balances speed and quality based on your specific application. Asterisk fine-tuning versus generalization asterisk. Asterisk trade-off asterisk fine-tuning Llama 2 on a specific dataset can improve its performance on tasks related to that dataset, but it can also lead to a loss of generalization ability, i.e., the model may perform worse on tasks outside of the fine-tuning dataset. Asterisk considerations asterisk carefully evaluate the need for fine-tuning and use appropriate regularization techniques to prevent overfitting. Asterisk open source versus proprietary asterisk. Asterisk trade-off asterisk Llama 2 is open source, giving you more control and flexibility, but it also requires you to manage the infrastructure and potentially handle more of the development and maintenance. Proprietary models, example from OpenAI, are often easier to use and come with support, but you have less control and are subject to their pricing and terms of service. Asterisk considerations asterisk evaluate your team's expertise and resources when deciding between open source and proprietary models. Llama 2's license makes it a very attractive option, but only if you have the capacity to manage the infrastructure. Asterisk latency versus throughput asterisk. Asterisk trade-off asterisk optimizing for low latency, fast response times for individual requests, can sometimes reduce throughput, the number of requests you can handle per unit of time. Batching, for example, can increase throughput but increase latency. Asterisk considerations asterisk determine whether low latency or high throughput is more important for your application and optimize accordingly. V. Advanced optimizations, beyond the basics. Asterisk speculative decoding asterisk a technique where a smaller, faster model generates candidate tokens, and a larger, more accurate model verifies them. This can significantly speed up inference. Implementations are emerging for various LLMs. Asterisk continuous batching asterisk dynamically grouping incoming requests into batches to improve GPU utilization without significantly increasing latency. Asterisk distributed inference asterisk partitioning the model across multiple GPUs or machines to handle very large models. Frameworks like DeepSpeed and Megatron LM facilitate distributed training and inference. Asterisk kernel fusion asterisk combining multiple operations into a single kernel to reduce overhead and improve performance. NDC/XLA excels at this. Asterisk custom CUDA kernels asterisk writing highly optimized CUDA kernels for specific operations in Llama 2 can provide further performance gains, requires significant expertise. Asterisk flash attention, and its variants optimizations to the attention mechanism that reduce memory bandwidth requirements and improve speed. Many Llama 2 implementations leverage flash attention. 6. Summary and recommendations. 1. Start small asterisk begin with a smaller Llama 2 model, example 7b, to get familiar with the workflow. 2. Enable CUDA asterisk if possible, use a GPU with CUDA to accelerate inference. 3. Optimize inference code asterisk use torch.no_grad, PyTorch, during inference to disable gradient calculation. 4. Explore quantization asterisk experiment with quantization to reduce memory usage and increase speed. 5. Monitor performance asterisk track the performance of Llama 2 in Porto to identify bottlenecks. 6. Consider serving frameworks asterisk use specialized model serving frameworks for production deployments. 7. Stay updated asterisk the field of LLMs is rapidly evolving, so stay up to date with the latest optimization techniques and tools. 8. Profile and benchmark asterisk always profile your code and benchmark different configurations to find the optimal settings for your specific use case. Remember that the specific steps and trade-offs involved will depend on the details of your Porto framework and your specific requirements. I hope this comprehensive guide provides a solid starting point for integrating Llama 2 with your infrastructure. If you can provide more details about Porto, I can give you even more tailored advice.